Awesome. I love starting off with stuff. Actually, okay, you can see this file face. I was really considering, like, starting stream off with, installing the drivers for my headphones again. Because, oh god, this desktop audio is a little loud for you, isn't it? There we go. Just bring that down. Yeah, that's probably better. Because I'm just so lazy. Like, I'm sorry, guys. I'm sorry I'm so lazy that I just can't. Like, and my mic does the weird wind thing, and it's so bad. It's so bad. I really should fix it, but, you know. You know what? Let me put up my little... I forget what my hotkey is for putting up my... That's not it. That's not it. Fix it. What is it? 2? Yeah, there we go. I'm put on my pointer today. Hopefully it's not too annoying. I just wanted to switch it up a little bit. See, I don't know, see how the white void treats me. Yeah, sometimes we can go outside for a little lecture, as you do. Let me just like see where my... Oh boy, okay. Let me, so it's like here. Let me just draw a real quick box on where you guys can see. What about this way? You guys can pretty much see, like, all of the vertical. Yeah. Okay. Let me just... It's gonna change if I zoom in or out. Whatever, it doesn't matter. Okay. I have it up on a different monitor anyway, so... Oh, sorry, I've broken the illusion. We're not completely in a white void. What do I have to do? That's a great question. So, I have many things to do. Some of those things include I have a midterm next Wednesday. Sorry, let me just cough directly into the microphone. Midterm next Wednesday for physics. So we got to do some work there on waves and other waves. Lots of signs. I have a midterm, not the next Monday, but the following Monday for math, for my good old calc. But I also have some homework for that, which is like due the next Friday. So, and I feel like, dude, I am so strong on all that stuff. The only thing that like is maybe a problem is if like I just get a volume problem that's hard to set up or something. But like when we do that homework, I'm gonna be bitching about how I'm like done with it after 2 problems, and there's gonna be like 20 problems. So I'm gonna be fine about that. I'm not really too worried about studying for that, because like the homework is literally so... If you don't get it by doing that homework, like I guess do more work, but it was looking into subspaces, pretty crazy. Subspaces are a little crazy. They are kind of hard to like wrap your head around. And it was really interesting. There was actually an answer. We were talking about we're talking about this. The question was about for a wait, switch to 5. For you know, some function, we could say it's like a circle. Let's put it in 3D space. You have some function, and you're trying to we'll just say it's like a space curve, right? You have some function, maybe there's like a hole here. Where the question was is like, for a gradient vector at a certain point, sorry, I kind of spoiled it. For a directional derivative at a certain point, what is the maximum directional derivative? And then what is when is the directional derivative 0? And so the maximum directional derivative, right, is just the gradient vector, so we don't really have to worry about that. That's sort of the definition of it. And we know that like the negative of the gradient vector is then the smallest the direction of the smallest slope. It doesn't tell us the slope, but it tells us which direction it's going. But like the question is when's the gradient vector 0, right? And this is kind of where subspaces come in, because the answer is like, right, if you take the dot product of this vector u, that it can be O actually for orthogonal, that we want to be orthogonal, that looks like a 0. Oh, we want that to equal 0, right? The answer is like, right, f1 01 plus f2 O2 equals 0, and this is a subspace, right? Because there's infinitely many things that can be this. Like you can have so many numbers. So it was kind of funny, but he was just like, oh, just pick one number, and that's right. And I was like, oh, I forgot we're not in linear algebra. The insanity in linear algebra aren't getting any better than calculus. I'm afraid, my friend, it is somewhat worse in linear algebra in many, many ways. I thought that, like, if you had trouble keeping track of things in calculus, you're gonna have not a very good time in linear algebra, because you just have like we didn't even do that much calculus, but it's just so much stuff to keep track of. And especially if you don't like just doing calculations. Like if you, oh my god, my current professor, it's so funny. He reminds me a lot of like my streams. Like I bet I could get him to do this and it would be like me streaming. He does make a lot of calculation errors though, like when he's doing problems. And I'm like, oh bro, like, dude, that'd be crazy in linear algebra. Like you just can't make that many mistakes. It makes sense because linear algebra is a 208, and then calculus is only 100 to 200. Yeah, it is definitely the next step up. I do think that linear algebra in some ways conceptually is easier, because it's algebra. Well, okay, it depends on if you're doing linear analysis or linear algebra, I guess. But if you're doing linear algebra, hopefully there's not too much calculus, except for maybe Wronskians. But that's pretty basic calculus. That's like calculus 1. Is you can do a Wronskian, which is just basically a matrix where you have a function as your 0, 0. So like if I wanted to do a Wronskian, maybe we have like e to the x. That's a really bad example. X squared, x cubed, x to the 5th. Then this would be like 2x, and 2, and then 3x squared, 6x, and then 5x to the 4th, 20x to the 3rd. Like this is just a type of matrix called a Wronskian. But that's really the only calculus I had to do in linear algebra. Unless you count, like, I kind of don't count vector stuff as calculus because it's vector. I don't actually teach a class because I'm technically not allowed to. I'm going to do that next year, but I'm a freshman, so they only let like sophomores do that. But I like tutor people from anywhere from basically like pre-calculus to like calc 3. So I hope you teach discrete math. Is that, wait, what is discrete math? I don't, have I done discrete math? I don't know. I mean, next quarter, I am gonna be doing linear analysis. So if you're having trouble, like there'll be a lot of stuff. I had a bunch of old streams on linear analysis, but that was before I was recording my VODs, sadly. So I don't think I have any of that, but like I had hours of like, you know, fucking kernel stuff. I remember root and elite. Yeah, I can post it. I don't have them. I don't have those linear analysis ones, sadly. But if you have linear analysis problems, like I can try and go through if you want me to do some. If you have any that are examples, if that would help. It might take me like a hot sec to remember, so I can't like lecture on it, but I can definitely take a crack at it, like if you think that would be useful. Like even like, I know you mentioned that you thought row reduction was hard, like if you have trouble with that kind of stuff. Linear analysis and linear algebra, are they the same thing? Yes, they are. So the difference is that linear analysis, at least my understanding, just goes like a little bit further than linear algebra. So when I took linear algebra, we were sort of just focused on like the building blocks. We were focused on like, you know, we were doing basically just like lots of subspace stuff, lots of learning about different ways to learn different things about matrices. So, you know, like determinants and fucking inverses, and then, you know, transposes and all the other things, and finding out if like subspaces were orthogonal to each other, all that good stuff. But linear analysis, from what I understand, is like more of a combination of differential equations and linear algebra. I think. When will I teach real analysis? I will probably not. If I'm gonna be honest, I think, especially when I actually do like get around to recording formal lectures, I think the highest I will go is probably linear algebra, because that's all that I'm actually going to be trained in, because I'm a mechanical engineer, so we're not required to take real analysis or any of that kind of stuff. That's more like math major stuff. But like, for example, linear algebra is really useful when you're dealing with systems of things, and you know that happens a lot in engineering. So I have that, but you know, comp sci takes a lot of math classes. Oh god, yeah. I have some friends in comp sci. Someone was saying the other day, I was meeting like some people, and they were asking about my major, and this one person was like, you should say you're double majoring in CS and EBI, and I'm like, oh my god, I could never. CS is like actually really mathy, and I am not really I could definitely do it, but the thing about it is like, I think linear analysis, like I think linear algebra you could teach yourself if you wanted to, but I think when you start getting into like real analysis, you have to kind of like, I feel like you kind of have to have a professor when you start getting into math like that, because it starts getting really like, I don't know how to describe it, like jargony almost. Like I tried to read one textbook on it and it did not go very well. I mean, I could always go again, but the thing that sort of interests me is like, you know, physics is very applicable, right? That's like using math in the real world. But a lot of things in math, like systems or even like stuff, you know, directional derivatives, all this stuff is like very, very, very applicable. But when you start getting to real analysis, you're talking about like the numbers themselves and like what they mean. Whereas I just want to like use the numbers, you know? Do I have to take abstract algebra? I do not. Yeah, I only have to take linear 1 and 2. Which is like basically differential. Linear algebra and differential. But I think they kind of cross over more in the middle. I think I'm... okay. We're gonna start with doing some chapter 16 stuff from this book. And we're just gonna hang the fuck out. Need to get to my syllabus. This is the wrong place to look at this, actually. Yeah, I don't have to take... I actually don't have to take a lot of math classes. I'm gonna be done with math by my first quarter of sophomore year. Which is pretty crazy, but it's because I was, like, ahead in math. I have to take more physics. I'm excited. We're gonna be doing a lot more physics stuff. But, like, for example, I could also be doing... I have some cool drafting stuff. You know what? We might actually be able to do that. Maybe we could do a drafting problem as like a fun it's like a break. I do my drafting homework as a break from my other homework, honestly. Let's see. Physics. Because there's a lot more, like, I have to take, you know, thermo, system design, and, like, a bunch of other stuff. Right now it's sort of just covering the basics and then going through and applying those. But my drafting is pretty fun. Okay, let's see. This is not a lot of problems, actually. I think we only have to do... I don't know how much of chapter 17 I have to do, but... we'll start with these and then we'll do some other stuff. Okay, so the first question is... what is the first question? That is a great question. I'm gonna snatch it from here. No, I didn't open it. Awesome. I honestly, like, for math and stuff, if I have time, I would take like a real analysis course. If I can take it with one of the professors that I like, because professor matters a lot in how much I can understand something, and it really helps that I have like a basic knowledge of all of the math that I'm going to learn already. So like Calc 4, technically I haven't done anything in Calc 4, but like I already knew partials before I took Calc 4. What about geometric algebra? I don't even know if we... let me see. Let me see if we have that as a class. Geometric algebra. Okay. Let's scroll all the way down here. Okay. Okay, so Math 404 here is differential geometry. Introduction to differential geometry. That means you take that your 4th year, so that's for math majors. We have complex analysis. So that's like complex numbers, I guess. Introduction to analysis. Oh. Differential equations is actually a different class than linear analysis. Let's see. Discrete mathematics with applications, game theory, topology, Euclidean geometry, modern geometries. Can you... let me see. Oh, you want me to like explain what they are? Let's see. Let's see. Okay, you're looking at... what are you looking at? Geometric algebra? Oops. calculus with analytical geometry. No, that seems like easy stuff. No, probability. Differential geometry, or because I think like for when you're talking about differential geometry, actually there's a guy who streams here who definitely has a lot more info because he's a PhD math major. His Twitch username, I believe, is literally just the letters RGPT. Let me check that actually. He does complex geometry stuff, I believe. It's sort of just like, yeah. I guess he doesn't have any videos. I don't know if he has saved his VODs, but he has very cool videos, and basically he goes through, it's like 3 guys, and they go through like different papers trying to like prove or disprove, or mostly just prove because they're like published papers. But abstract algebra, let's see, what's that? Linear algebra from a theoretical point of view. Oh, that looks like linear algebra from a theoretical point of view. I don't see how. Okay, maybe that's just more like proofs of stuff, because I don't really see how you could do linear algebra from a non-theoretic point of view. Like when I learned linear algebra, it wasn't just all numbers. I mean, we did numbers stuff, but maybe it just means no numbers. Very interesting, very interesting. All right, let me see. Okay, let's do some of these problems here. What do we got first? Pull this over here. My school has, what's the highest math you have to take for comp sci? I don't know, it depends on your university, I think. I know that like my school has a, sort of like a degree planner, or like a degree map. Linear optimization, okay, yeah, I mean that sounds right. I don't like system design, which is another reason I didn't major in comp sci. It's because it's kind of like, like I took a data structures class and they started talking about big O notation, and I was like, nope, sorry bro, I don't want to do that. That was the point where I noped out. But you know, okay. Let's do a little bit of physics here. Okay, so we got okay, you can't see that. We got a 25 gram, that's not 20, wait, yes it is. Okay, 1, 2, 3, wait, fuck. 25 kilogram string, so 25 grams. Equal mass. And then tension equals, wow, I don't know why I wrote that. Force T, I guess, is going to be 20 newtons. A pulse travels the length of the string in 50 milliseconds. So from here to here, the speed of it, okay, so like we want V. Transpose is hard. Do I remember how to do the transpose? Transpose. Oh, it's in my brain. Oh, it's so close. It's on the tip of my tongue. What's the transpose in linear algebra? Oh, no. Okay, it's not that hard. I was thinking of something else. Transpose is just like you take the rows and switch them into columns. Okay, transpose, I'm not gonna say transpose is easy. It is a little, like, hard to visualize. How can you take linear algebra before calculus? Okay, that's a great question. So, the reason... Okay, at my high school, we had a bunch of people, including me, who were like a year ahead in math, which is not that uncommon. But what it meant was that there was like 12 of us who would basically take calculus BC, right? So we took it like junior year. And then they were like, oh, we don't have any more math for you to take. Like, we can't take, you know, you can't take AB because that's like, that was sort of like the easier calculus to take, and then people would take BC, but, or just take no math their senior year. So they had classes taught just for like one class, basically. And every other year, they would teach either multivariable or linear algebra. But the problem was, is my class, we took BC, but we didn't take multivariable, because there were some people who were 2 years ahead. I also forgot to mention that. There's some people who were crazy ahead. So they needed to have these two classes so that those like people who were crazy ahead could like take two classes. But they didn't really think about like the 1 year people, because I hadn't taken multivariable, but then I took linear algebra. So that's why I took linear algebra before. But I do think that like, I do think that you should learn linear algebra before you learn multivariable, just because it makes a lot more sense. And then you don't have to like go back in linear analysis and like teach how to apply it, because a lot of the stuff in, like, there's so much vector stuff in multivariable already. I wish I had a high school teacher to teach me calculus and linear. Yeah. I was very lucky. I did go to a school that was like kind of known for its STEM side of things, so this distance over time. So this is going to equal length over that 50 milliseconds. Milliseconds is what? Milliseconds to seconds. 0.001, so 0.50. And then we can use our wave speed, v equals the square root. Oh, do we have a density? Or are we just flying by the seat of our pants here? Oh, of course we do. They gave us a fucking thing. Okay, so v equals the square root of ft, so 20 newtons, divided by m over l. So that'll be 0.025 divided by l. And then this whole thing is going to equal, and I'll just square it like right off the bat, because why not, you know? So this will be L squared over 0.0, do I have a phone on me? 1 sec. I'll be right back. My back is so sore from dancing. I had a performance yesterday, and then I had to use the heaviest lion in practice today. My captain was not kind, but no, he was actually really nice today. It was really good, but I'm so sore. Calculator. 0.05 squared. 0.025. Equals 20 over 0.025 over L. So I'll rewrite this to be 20L over 0.025. This cancels with this. This cancels with this. So L equals 20. 20 meters? Huh? No way. There's no way that's 20 meters. Dude, that's so long. And this string, the pulse goes in 50 milliseconds? No way, right? No way. No way. Oh no. That's gotta be wrong. That's gotta be wrong. Oh god, chapter 40. Sorry, I'm just scrolling up to see the answers. 2 meters. How did I get a decimal point off? Oh, because there's a decimal point there. Yeah, okay. Okay. That's just the math. Okay, so yeah, this one is divided by 10. Which one is divided by 10? What is 0.025 divided by 0.0025? Oh god, I didn't put... Oh god. 0. Yeah, it's 10. Okay, so 20 divided by 10. Cool. 20 divided by 10. There we go. That's much more reasonable. At least I was order of magnitude right. Okay, cool. I was like, oh my god, that's really long for a string for one of these problems. Okay, 10. Ooh, exciting. So it's an angular frequency, so omega is 30 rad per second, and a wavelength, lambda, equals 2 meters. That is the worst lambda I've ever drawn. Let's do a little, there we go. What are its wave number and wave speed? Okay, so the wave number is going to be that 2 pi over lambda equals, well, pi. That's just a number, I'm pretty sure. Doesn't it? Units? Oh. And then this is 2 pi. Okay. Okay. Thanks, computer. This is 2 pi f. So f equals 30 over 2 pi equals 15 over pi. Because we're going to just go v equals, watch this, lambda f equals 15 over pi times pi equals 15 meters per second. And look at that, we don't even have to plug anything into a calculator. I love it when that happens. Just a clean problem. Oh, it's so clean. So nice. Beautiful. Cool. Cool. Awesome. Awesome. Cool. Just NPC dialogue. Okay, 14. Oh, fuck off. Sorry, that was rude. There's a picture. I'll get it for you guys. I'll get it for you guys. It's probably better to have the picture in here anyway. Here we go. Wow, that was actually really easy. Okay. Amplitude, frequency, wavelength. Okay, so we can get the frequency real quick. 1 over t. So we look at this, we say how long does it take to go from here to here, and we see that's 0.6, so 1 over 0.6 equals, I don't know, 10 divided by 6? I could just do 10 over 6. Is that 10 over 6? 1 2/3, which is 5/3, yeah. That'll be nicer to just keep as a fraction, I think. And then the amplitude is going to be up to 6 centimeters, so 0.0006 meters. And then our wavelength is going to be, let's see if I can remember it off the top of my head. Oh, we have a wave speed, so I think this is from this graph. Yeah. Okay, so v equals lambda f. So 2 equals 5/3 times lambda. So we multiply this over 6/5. Right, so 3 times 2 over 5 equals lambda. Nice. and that is in meters. Does that kind of make sense? I feel like, yeah. I mean, it's going like in 0.6 seconds, it's going a full wavelength, so I assume it'll probably be pretty fast. Ooh. Okay, maybe this won't be too bad. I think the sort of thing that I'm nervous about is, like, we have some stuff we did in class, but we have some stuff we didn't do, like, in lecture. And I think he's testing us on all of the stuff, but, like, I don't know, it's kind of up in the air, which is never something I want to say about, like, an exam. Okay, 17. Ooh, we're already doing sound and light. Awesome. What is the wavelength? Oh, I did this one. This is kind of silly. This is a little silly. So, all right. We're looking for lambda equals what if frequency equals 2 megahertz. So that's going to equal 2 times 10 to the 6th. Is mega 10 to the 6th? Mega 10 to the what? 10 to the 6. Yes. Okay. And then we need a V equals something. And I'm blanking. What is this? Sound traveling through aluminum speed. Wait, do I just use... What the hell is... Why is that like that? 6420 meters per second. 6420 meters per second. So then 6420 over 2 times 10 to the 6th equals lambda equals what? Two times 10 to the 6th. 0.00321. Wow, 321. That seems that's in meters though. Let's check that. That seems a little oops, I don't know why I saved that. Okay. This is 3.2. Yeah. Nice. If I had a thumbs up, I'd be doing a thumbs up right now. I mean, I do have a thumb, but I can't put it up because my arms, they work, they're functional, as you can see, but I can't do a thumbs up. I got cursed that I could never do a thumbs up ever again. Sadly. It's tragic, really. And we also have to say if... what frequency would have the same wavelength? So if the wavelength equals this, so lambda equals 0.00321, then V equals 3 times 10 to the 8th, because this is an electromagnetic light wave. And we're looking for F equals question mark. So 0.00321 over, wait, I lied, V. Let me just switch this out. This, and then 0.00321. Oh god, 2 million. That's 2 times 10 to the 1, 2, 3, 4, 5, 6. 10 to the 6th? 7th. 10 to the 6th? 10 to the 6th. Wait, what? Oh. Okay, this is a different... this is saying 9.3. What did I get? I got... Oh, it's because I'm doing the wrong thing. That would explain it. Yeah, okay. Oh god, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Times 10 is 9.3 times 10 to the 10. There we go. That's right. Me hurts. Hurts. Cool. 24. I am really glad we don't have to do thin film interference though, because we were about to have to do thin film interference and I don't know if I could take that. That was one of the worst questions the AP ever decided to add in. They were like, oh, you should do thin film interference. Just casually do thin film interference. No. It's just like man, why? I don't even remember. I think it's, wait, let me see. It's like when something goes through something really thin, it like when it reflects back out, it like phase shifts. It's so weird. I mean, it's really cool because it's what like makes bubbles look all rainbow, but to figure out, it's just really kind of a slog. Okay, how long does it take light to travel through? Okay, so we're asking about a time. How long does it take light to travel through a 3 millimeter thick piece of window glass? Okay, so the speed of light in glass, we're gonna have to look that up. Light speed in... Actually, maybe they gave it to us. Light speed in glass, you gonna give that to us? No? Okay, awesome. Google it is then. Light speed in glass. That is... Instead of 3, it's 2 times 10 to the 8th. Very, very important. Big difference here. And the piece of window glass is going to be... I guess I should just maybe say, yeah, length equals... millimeters, so that's 0.003. Now let's see if there's any equations here, because kind of seems like mayhaps that is an equation that I just don't have. This would be for waves. We're looking for the time it takes something. Oh, wait, what am I talking about? This distance equals speed over time. So V equals... Speed equal... Okay. Speed equals distance over time. Oh, my brain. Sorry. Distance over time. So then time equals distance over velocity equals 0.003 over 10 to the 8th. 2 times 10 to the 8th. Hey, Vintage Luigi. Oh, I saw your question about the zeros. I feel like it would be an infinite amount of zeros. Is that a right answer? Can I answer that? 1.5 times 10 to the negative 11? What the hell? I guess. What's like a microsecond? I'm trying to think, because like the answer that is like if it's a countable 100, wouldn't it be infinite zeros? But I guess I can't really see any other way that it wouldn't be like infinite zeros. But maybe I guess if you added it, because like the one thing I do know is that like if you actually take the series of 1.9 or 0.9999999 repeating, it turns into you know 1 technically in math. Wait, do you mean the decimal places or the zeros to the left of the decimal place? Let me see what you said first, because I may have read it wrong. You said how many zeros are at the end of 100? Number of zeros to the right of the most non-zero digit. I was asking, yeah, okay, so infinity plus 2, because like don't you have infinite decimal places? It wouldn't just be 2, right? There's no way it's just 2. But I guess if it's a countable 100, you can't have like 100.000 chairs, and it's just 100. I mean countable in the sense that like scientific, what is it called? Sig figs? Significant figures? Sig figs. Seems like a theory where you'd have to count, seems like a number theory problem where you'd have to count the factors of 2, 5, and 10? What? Wait. Sorry, the only thing I can think about is that's just a theory, a number theory. Thanks for watching. If MatPat did real analysis videos, I would watch his videos. Bro could save his channel by stopping talking about how many FNAF children there were and talking about Lagrange multipliers or some shit. The soup of a function, the supremum. It's a classic number theory problem. I'm so shit at number theory. I genuinely am so shit. It's crazy to self-learn linear algebra. Let me see if I can get... Okay. I don't remember if Paul's notes is only differential or not. So I have, if you want me to send you my notes on stuff, I can actually just take pictures and send you my notes that I have, because I know you don't have like a teacher. Oh. Oh no. Okay, wait. I don't want to like give you like a fucking virus link. But this is a Reddit thread on Paul's notes for linear algebra. He is a really good teacher. Oh wait, here. Oh, here we go. Never mind. Don't click that link. Well, I mean, you can click that link. It's just a Reddit link. This is the PDF. He's awesome. I really like his differential stuff. You have to take the class to know it, unless you're Fermat. I'm assuming that's the guy who is like Fermat. What's French? I don't know French. I've always just like been really bad at number theory also. Oh no, sorry. I was reading vintage Luigi's comment there. You don't need to take a class to learn linear algebra. You can learn linear algebra, you're fine. I could probably teach you linear algebra if I was not so busy. But I would click on that PDF and use that because it's a really good PDF. Although, like, okay, it depends on what you're using it for. Like, for me, I would highly, highly recommend people who are going into engineering to take classes that are actually, like, taught by a professor about calculus. Just because the logistics of it would be really, really hard to make sure that you were clean on stuff. But if you're using math as sort of a not a tangential thing, but if you're going to be taking classes that show you how to apply the math differently in your major or whatever, your field of study, I think it's a little bit less necessary that you like definitely need to take Calc 1 like out of college or something. But if you're an engineer, it's like it is kind of worth it to just be like solid on it. At least that's my opinion. Although I know a lot of people who do take classes who don't become solid on it, you know. Through what thickness of water could the light travel in the same amount of time? Okay. So we take this time then, this is A. And we plop the time in here. And we change our V to light in water. V light in water is 2.26 times 10 to the 8th. We could calculate this out if anyone is interested if we were to use Snell's law. But we're not going to do that. So length equals VT equals 2.26 times 1.5 times 10 to the 8th times 10 to the negative 11. This is going to be just a little bit. That's comforting, though, to know that this works out. So 2.26 times 1.5 to negative 3. 10 times 10 to meters. Yeah, that's chill. Just a little bit less, a little bit more than the other one. Which makes sense, because the speed is a little bit more than the other one. Alright. 33. Okay, we should do some of these as well. Wait, the only question I do have... Okay, I'm not going to scroll all the way up in this document because it's going to take me a million years to scroll back down, but there are some other things like resonance and stuff that I don't think we were assigned questions on, but I think I'm going to go back and read. Although I don't think he would test us on it if he didn't assign homework on it, or if he did, it might just be a conceptual thing, but, you know, what are you going to do? It's pretty cool though. He did a demonstration. Physics classes with demos or labs are always the best in my opinion, but he did a demonstration of the Doppler effect where he like swung a speaker around his head and showed that it like changed pitch, which is pretty dope. That, and then like we did a lab where we had like a string and a vibrator machine that like used an electrical signal to like make this like go in and out, and we were doing like superposition, so it was like we had to find like where the nodes and antinodes were, which was pretty dope. Also, it's crazy that like you can make standing waves. I don't know, I just think it's really awesome. I'm not really a physics. I was gonna say I'm not really a physics guy. I literally am streaming physics, but I think that's pretty cool. Okay, so we have an intensity that equals 2 times 10 to the negative third watts per meter squared. So intensity, right, is a power of a wave spread out over a certain area. So it's a wavelength, like the energy, right, if it's concentrated versus if it's, you know, like this, it's going to be more or less loud. Your eardrum is, which is perceived to be modestly loud. Your eardrum is 6 millimeter in diameter, so diameter. So let's do radius then. 0.003. How much energy will be transferred to your eardrum while listening to this sound for 1 minute? So T equals 1 minute. Okay, so I is going to equal, intensity is power over area, and power, if we have taken any sort of electromagnetic based or electrostatics, you'll know about power. But so we've got an area we can do. So area is going to be, I'm guessing an eardrum is just a circle. I don't really know technically. It's probably like this, so it's probably not really like perfectly a circle, but we'll do that. So we are asking how much energy. So we know the intensity is 2 times 10 to the negative third, and that's going to equal, we'll bring the t down on the bottom. So energy, well, we don't even need to bring the t down on the bottom because we're going to flip it over. So this is going to get yeet over here times TA. Now, the only question is we got to turn time into seconds. So that'll be 60 seconds times 4 pi, nope, 2 pi r squared. Wow. Rough day. Rough day. Times 2 times 10 to the negative third. And that's going to equal our energy. Look at that. No equation sheet. Look, Ma, no equation sheet. Okay. 60 times pi times 3 squared times 2 times 10 to the negative third. Okay. It's a little number, which seems kind of wrong that it's a little number, but I guess your eardrum is pretty small. So, is there anything that factors in how far you are away from it? Nope. Nope. No, nope. I guess not. But we can check this one. Oh my god, this is 27 over 25 million times pi. Such a funny number. Anyway, sorry. 3.4 times 10 to the negative 6. And this is an energy, so it's in joules. I really need to get used to doing my J's like this, because in engineering, gotta do that. Let's see. This was problem, what was this? I don't remember, 33? Paper 4 times 10 to the negative 6! Let's go! Gamers! Gaming moment! Gaming moment! I love it when I headshot the equations. I guess it's not really an equation, is it? It's just like a problem. You know. You know, we do a little trolling. We do a little winning. Okay. During takeoff, the sound intensity level, so the loudness of a jet engine, is 140. I'm going to just say loud equals 140 decibels. At a distance equals 30 meters. What is the sound intensity level at a distance of 1 meter? Loud 2 equals, from 1 kilometer. So 1 kilometer is 1,000 meters. All right, this one I'm gonna have to look into equation for, but it's okay because we have that. Let's see. Okay, so I guess that's just the radius. Wait, no, what is the equation for... Do I know off the top of my head the equation for... Oh, no, we're good, we're good. I was gonna say, I don't know the equation for intensity level. So it's beta equals 10 log 10 of... the ratio of the sound to... Huh. We did prove this. I remember proving this. It's an inverse squared relationship. But How do I guess I don't have an equation for it. I don't really want to have to derive. There's no way I have to, like, take a... Like, I don't have to raise this to the power of e to figure this out, right? Hey, what's up? Not much. I'm just chilling out. How's it going? Having a little drink, a little sippy. I hear talk of decibels. Yeah. We're doing sounds. We're doing loudness. I don't remember if you have a certain loudness and then you move away from it, how to find that new intensity level. I'm going to have to grab my book. Unless you know it off the top of your head and you could flex. That would be kind of cool if you could do that. Definitely not because I just want to take your answer. I'm gonna get my book. I don't remember how we proved it. Because I don't remember if it was like using... I don't remember. No flex this time? Aw, no big flex? Okay, that's fine. I think it has to do with the distance from the... Oh, wait, am I like... Okay, maybe I'm just like... Okay, wait a second. Before I go get my book. Okay, this is my hypothesis. Here's the jet. I'm gonna draw him with a happy face on it. That looks a little strange. Never mind, now it's a plane. This is not accurate. He needs to be yelling, okay? There's his mouth. He's yelling. Much more accurate. He's yelling and he's sending out waves, and here, at 30 meters, the loud equals 140. So we know that it should be getting quieter when we go out. ... 1,000 meters. Okay, can you explain a subset? Okay. So there are two different types. Let me do one thing. I'll be right back and then I'll explain that. Okay, so the reason why I went to go get this is because I don't want to give you the wrong information. And so in linear algebra, linear analysis, what have you, matrix stuff, there are two different types of things that are very close to each other. And one is called a subset, and one is called a subspace. If I remember correctly, a subset is a... Let me see real quick. Okay, a subset is just a selection of vectors, right? So you have a vector space which contains some vectors. If you say like, okay, this is the vector space Rn, or let's get a little bit easier, right? Let's say all vectors that have 2 dimensions, R2, that is a vector space, right? It contains some vectors. If we say, let's have all of the vectors that have that are multiples of, that have like multiples of 3. Like, so if you can divide both by 3, we want to just look at all those vectors. That is a subset, right? So we're just defining some way of looking at vectors. Now, subspaces are a specific kind of subset that follow certain rules. So to define something as a subspace, first off, it's got to be a subset, right? You got to explain what kind of vectors you're looking for. But it also has to be what we call closed under addition and scalar multiplication. So that means if your vector form can't be follow the addition rule or the multiplication rule, then it doesn't count as a subspace, it only counts as a subset. So, for example, if you have the subspace A, 2A, 3A, 4A in R4. That is closed under addition and scalar multiplication, so that counts as a subspace. Does that make sense? Let me do an example of what a subspace is. Here, I'll actually just do that example. So to prove if something is a subspace, right? So a subset, you can kind of think of it like this. This might help. So you have some big vector space. This is your initial thing. Actually, we can do it even better. Here, okay. Let's say you have a cookie, right? This cookie is your vector space. This cookie contains a bunch of vectors. And they're like chocolate chips in here, right? Doesn't really matter. They don't really have to have any connection. They don't even have to. They could be whatever. They could be like M&Ms too. Like they could be different kinds of stuff. And let's say we want to say, okay, all the M&Ms. We just want to look at all the M&Ms, and we just want to draw them all out and kind of group them together. This is a subset. We're just choosing some things that are in here to look at. But if these M&Ms all follow like a certain kind of rule, let's say like they're all red or something, now that's just an arbitrary rule, right? Our subspaces also have arbitrary rules, or known rules, I guess I should say. They're not arbitrary. Then they qualify as a subspace. So you can have a subset of vectors that's not a subspace of a vector space, but that's sort of how you can visualize it. So if we look at the subset, which is a subset of R4, which is A, 2A, 3A, 4A. We want to see if we can prove if this is a subspace. So the way we can prove that is we have to prove it under addition and multiplication. So to prove it under addition, we need to add two vectors in the subspace and see if that resulting vector is still in the subspace. So the way we're going to do that is we're going to have U equals A, B, A, 2A, 3A, 4A. And we're going to have V equal B, 2B, 3B, 4B. So we see we're kind of just plugging in whatever value for this, right? And this could be like, we could have something that's a vector W that's 1, 2, 3, 4. That's still in this subset. But we want to check. So we're going to do U plus V. So it'll be A plus B, 2A plus 2B, 3A plus 3B, 4A plus 4B. Now looking at this, it might not automatically seem that this is sort of like the form that we want, right? But if we factor this out, we get A plus B, 2 times A plus B, right? 3 times A plus B, and 4 times A plus B. So we know that that is closed under addition, so we can give it a little check mark. You can see that check mark right there. So now we got to check if it's closed under multiplication. And what that means is if we need to let K be a constant, right? We want to see if you multiply this vector. Wow, that was shitty writing. If you multiply this vector by any number at all, is it still in the subspace? Because that's the definition of subspace. So we're going to try doing this. K times U equals what? We're going to get, oops, I put that the wrong place. Ka, 2Ka, 3Ka, and 4Ka. This one's a little bit easier to see because of the way I wrote it, but you can see that this A now has turned into Ka, and that's here and here and here, and that follows our form, so that also gets a check. And now we can say that A, 2A, that's not a 2, 2A, 3A, 4A is a subspace. So one of the hard parts about linear algebra is that there's a lot of very specific terminology, right? So it matters whether this is a subset or a subspace. And you just kind of have to get used to the language that they use. If you ever have any questions about any of the language, feel free to ask me and I will do my best to explain them, like if you want to DM me. because Lord knows I had issues with, like, what does actually spanning mean? Or, like, what is the vector subspace that all vectors reside in? You know, so... But yeah, that's sort of the basic concept of a subset versus a subspace. And you get a free explanation about subspaces, too. Hopefully that helps. Okay, back to loudness, with this spooky music. Okay, what I'm thinking. We have one intensity. We have one intensity for both of these. They share the same intensity, right? The only difference is the area it's spread out over. So we're gonna say intensity 1 equals, we're gonna use the same thing we did, right? So the power is gonna be the same, it's energy over time. And the area is gonna be pi times 30 squared. Now intensity 2 is gonna equal power over pi 1000 squared. So we need to figure out how many times this is different than this one, because then we can apply that to the loudness. Because if we look at our loudness function, just quickly, you guys can't see it, but that loudness is going to be... actually, is that true? I might not be able to do that. Because it's not directly, like, loudness is not directly proportional to intensity. Like, if you take the log of, like, you can't just say, oh yeah, if you go 2i, it gets 2 times louder. No, it gets log 2 times louder. Oh, I guess we could just say that. But not really, because you can't split logs up. Much to think about. I'm stroking my non-existent beard. Like Pinot would. I think it's oh, I guess I could just check how we did it in class. That would be the smart way to do it. I think we just proved it with ratio sizes. Sorry, the ratio of the radii, but I'm gonna go check that. I like how I have to get every single notebook I own whenever I stream. Like, you'd think I just would have them, right? You think I would just prepare them beforehand at this point. It's okay, I'm back. Okay, that's superposition. That's not what I need. Superposition's so dope, dude. But it's also like... I don't know, I'm kind of tired of waves already. I've done a lot of wave stuff. Okay. Oh, hey, look, we did this problem. Oh, except they gave us they gave me the intensity for that one. Wait a second. Oh, it's a sphere. It's not a circle. Oh, woof. Okay, I will do that. I will remember that in the future. Yeah, it's not pi r squared, it's 4 pi r squared. But that's just, you know, I'm off by a 4, so... So, the thing we did was then 2 equals that. We solve for the power, but we can't... Oh. Aha. Okay. We can implicitly do this a little bit. We can do this. And then we can put this in here. But again, we don't have a... Oh, okay. Maybe what they think I just figured it out. Okay, I think what they want us to do is use this to then get an intensity to then put into the other thing. That's a little sus. Okay, fine. 140 equals, well, I'll just do 14 because you automatically multiply by 10. Log 10, log base 10. Yes, everybody, you heard that correctly. Not an ln, log base 10. Fucking crazy, actually. Over, 10 to the negative, wait. 10 to the negative 12. So that means e to the 14th equals 10 to the negative 12 equals I. I love that answer. That's awesome. That's an awesome answer that I just got. I'm not salty at all. So dope. I love physics so much. I love that it gives me ease. It's not annoying at all. It's great. Everything's awesome. Life's great. Okay, stop bitching. Okay. Then we just put that in there. And then we just put that in there. Look at that. 4 pi. Cancels. Get out of here. 30 squared over 1,000. I guess I could just do this. 3 over 100 squared. We're doing the math. We're doing the math. We're doing it faster. We can get better. It was I1. And then we plug in I1 because we found I1, which is e to the 14th times 10 to the negative 12. Everyone's favorite number. How do you not love that guy? And of course, this is a problem that I can't check. So thankful for that. I just love it when I can't check problems like this. Awesome. Great. Okay, 2 point... Was I trying to find? Wait, I found the... What is... So it says... Wait a second. Oh, no, I need the intensity. Okay, so... I2 equals 2.17 times 10 to the negative 8. Why is that bigger? Wait, is that big? I can't tell. No. E to the 14th should probably make it better over there. I was like, why is this so bad? Like, why is this one smaller? This one should be louder. Okay, it is louder. He's like 3, so it's on the same order of magnitude. It probably comes out to way bigger. Anyway. Then we have to plug this into the log function. So beta equals 10 times log of this garbage. But bonus points, we kind of get a little bit of extra oomph there from that 10 to the negative 12. So 2.17 times 10. Nope, divided by. Very important distinction. Cool. And then this, and we take the regular, the regular log. Okay, sorry. That's 10. 43.37. And everyone applauded. I don't know if that's right. But we're gonna say it is, baby. Hell yeah. I'm cool with that. That seems like, you know, you go out like, what is that? How much bigger is that radius? How many times bigger? So 30, wait, 1,000 divided by, nope, not times, divided by 30. That is 33 times bigger. So the intensity should be, what is 33 squared? Should be 1,000 times like smaller, which is probably real. That's probably true. Like 3 powers smaller. I wonder what e to the 14th. E to the 14th times 10 to the, whoops, 10 to the negative 12 equals. It actually equals to negative 6, so yeah, about 2 orders of magnitude off. But yeah, That's kind of cool. It's kind of cool that they did that. Anyway, let's see. What time is it? We've been going for like an hour 20. I kind of want to do some drafting. Do you guys want to do some drafting? Should I just take a picture of one of my drafting things and we can hang out and do that for a bit? Drafting is so chill. What's a drafting one that kind of sucks? Well, I'll have to do them again, like, because all of the work is physical in this class, but this one I did already. Oh god, I have to fix the circle on that one. Woof. So, my lab yesterday was on holes. It was on holes. I had a vibration lab and a hole lab this week. Love to hear it, right? Hell yeah. I don't know, which one like looks like it sucks a lot? I'm realizing I'm blocking the camera. Oh, this one looks like it sucks a lot. Oh yeah. Oh yeah. Oh, we have to use the measurements shown too? Okay, good, the scale's 1:1. Okay, chat. Okay. That's rough, dude. Oh, I'm gonna have to like measure it out. Okay. This is kind of okay, because I'll just do a little sketch of it and then we can go back to doing physics. I don't know, just have a little fun with it, right? Just goof it up. Goof it up. Be a goofy little guy. I need to send that to myself. Doing drafting work makes me sane again. After physics problems that I can't check answers to. Basically, if you don't know what drafting is, it is for when you're designing parts for engineering, if you're doing like patents and stuff, you're required to sometimes hand draw, sometimes like you can do it with SolidWorks or other CAD software, but you need to have like a top, side, and front view of your part. So we draw them by hand for this class, and it's pretty chill. I think it's relaxing. Some people find it really frustrating. I don't know why. Okay. Okay, the part, I'll just put the part up there and then we can just do it down. This is like what my major actually does, not just physics. I feel like so many people, like I feel like probably like at least 80 or 90% of people just think I'm a math major. I think I might have updated my description or something after like a bit ago, because I was like, I am not a math major, guys. Like no shade against math majors. Like y'all are awesome. It's just like this is normally the work I do. It's stuff like this. Or I have a turning class, so I just turn stuff on the lathe. Like, I'm not only doing math. I smell popcorn outside. That smells good. Okay. So, okay. I don't know. I kind of want to start with this face. So I'm just gonna sketch out. Okay, well, first off, one of the most important things to do is choose which side. Well, actually, never mind, this is an isographic. But sometimes you have to choose which side of the part is more like the front. Like, so you have to choose which one gives you the most information about it. And this shape is pretty crazy, so that's probably a good thing to choose for the front. Okay, so this is gonna go all the way up. And normally when you're drawing stuff like this, you have to use rulers and all sorts of other things, but this is sort of just a little nice, relaxing drawing of it. So let's see if there are any other faces here. So we've got this, then this face is also going to show up, right? That's a triangle. This looks like it goes all the way back, so we don't have to worry about that. This comes out to roughly, it's probably in line with this, I'm gonna guess. But we measure that. So yeah, that's pretty good. I think that's all the faces. So yeah, this one, this one, this one, and you don't have anything else. One other thing we have to do is we have to add the hidden lines. Which, let's see, are there any hidden lines? Probably not. I lied, there are. There's a hidden line back here, because this is a face that gets made, and that drops down to here, roughly. This is not a hidden line. This screw is going to make a hidden line. That is counterboard, so it's going to look something like this. I'm guessing it goes, does it go all the way through? That's the counterboard part. I'm gonna say it goes all the way through. There might be some stuff on the drawing that's like, that doesn't go all the way through, but... Okay, so then we have to draw a side view. So one of the cool things is... Well, one of the nice things about being on a computer is I can just add a ruler so I don't have to deal with trying to draw lines. But we can draw some construction lines in because we have to draw the side of the part. And we're gonna... Any line that, like, is parallel basically here is gonna show up on that side view. So let's start with... Okay, I also need to add... Let me just quickly add our vertical line over here. Like that. So that'll tell us how far the part is apart from the other part. Okay, I gotta turn this ruler off, actually. Here we go. So our first face is this one, which is gonna go from here to here, so we'll just do it like here. And that goes all the way across. Some length. You know, you gotta measure the length, but right now we don't need to do that. Actually, I lied. That doesn't go all the way across like that. It actually goes across like this. See, I forgot to extend this line out. That's gonna go across like, probably like this far. And then we're gonna have another face go up like this. Because that's this face on this view. And then one that's probably like in the middle. I'm just guessing because, you know, I can't measure, but whatever. And then we also have this, this one back there, which is going to come down like this. And that'll be that line. Okay, so that's pretty nice. We've got that going on. Now we have this face here, which is going to be, it's going to look like, what's it going to look like? Well, this side is going to come up. And there's going to be an angle here of some kind, right? And then a line down. That's pretty good. Pretty fairly accurate, I would say. Right, draw that on the circle. Draw that one into. And then, like, you have to erase all the construction lines after. The only thing we don't have is that screw hole, so we would just project this sort of across as well, and then like that. And then the last part is, and oh god, thank god I can move things. God, I love digital so much more. Oh, let me move that as well. Not that, I lied. It's this. So then we have to, and normally you would extend this up, and then extend like this up, and this up, and this up. And you would actually draw like a 45-degree angle here. That's not really 45, but then you would extend the back of the part up and then go over, and that would give you your top view line. None of that is accurate. So, or you could just measure this distance and just put that distance here, which is what I could do here. And then just go across. as sort of, you know, as a construction line, but I don't have a construction line like that. Okay, and then we just project these up. And so our top view is going to be some sort of height also. That's the one thing that we do need to measure, like the depth of it. But we'll just sort of guesstimate it to be like there-ish. And then it comes across all the way. It's nice, little box. And now we have a lot of stuff on here, a lot of hidden lines. But we can do the non-hidden lines first, because those are kind of kinder. This is going to be there. Right, and then that actually looks like it goes over and then another angle, sort of like that. I mean, I didn't really draw it well, but does not look like it's like, oh no, it's not angled like that. That's a different angle. It just goes like here. And this face is angled. And then we have this corner over here. Starts from the same place, goes, you know, a little bit up like that. Our hidden lines, which will be bringing this back, bringing this back. Those cuts. What else have we got? And we have that nice big circle that actually gets to be a circle here. And we sort of draw the center of the circle. There's actually another one inside it, right? Because it's counterboard, so. Lovely. Anything else that I'm missing? Oh, actually, that's why this looks so weird, is because there's a plane here that is like that, I think. So yeah, that's like what I do for classes when I'm not streaming. Stuff like this. Stuff like drawing parts, if anyone is interested. It's pretty cool. I like it. It hurts my back though, because I gotta bend over a table. Or I gotta like punch over a table, I should say. Let's do a couple more physics problems. And then I think I'm gonna wrap up. I didn't do any math. God, I have to do math, but I think anything will be better than just doing like 40 partial derivatives. Although min-max problems do take a while. They're kind of one of those things where at least you can actively think about them. Because the two sections are minimum and maximum with, I want to say it's minimum maximum with mostly 2D functions with a third sort of temperature function. And then I think the second one is min-max with however many variables, and that's Lagrange multipliers, which are really not too scary once you get to know them. I was a little worried about them, but they're pretty chill, honestly. I think they're mostly nicer than solving things the Calc 4 way, or Calc 1 way, which is like you just take the partials and stuff. Anyway, that was kind of fun. I don't know, sometimes you just gotta do a little drafting in the middle of stuff, so you don't lose your brain. Okay. What was what I was doing? I don't know, let's do like 2 more, 3 more. I don't know. It depends on how hard they are. The one I just did was 36. Yay, one we can check. Yippee! I love being able to check problems so you guys can see that. Oh, we'll just put it here. God, I love being able to check just having the answer and no like explanation check. Oh, beautiful. Oh wait, we did this problem in class actually. This is so funny. Okay, I actually really like this problem. So, okay, bats locate insects by emitting ultrasonic chirps and then listening for the echoes from the bugs. Suppose a bat chirp has a frequency of 25 kilohertz. How fast would the bat have to fly and in one direction for you to just be able to hear the chirp at 20 kilohertz? So F1, F2 equals 20 kilohertz. This is the source is moving. So this is a Doppler effect question. If you're unaware of the Doppler effect, basically the way that waves are emitted, they're sort of emitted like this, right, around a source. But if that source is moving, as it moves, the waves it's going to emit are going, here, I'll draw them a little bit better. So like the closest ones emitted this, the other ones emitted, like these waves are sort of traveling outward. They're not really supposed to, actually I lied. They're not supposed to cross like that. I didn't space this very well. Basically, the waves just kind of bunch up. Oh god, that was poor spacing. Sort of like this. There we go. There we go. That's a real Doppler effect question. So like your source is moving along here, and it was here, and then it was here, and then it was there, right? So the waves bunch up, so the frequencies get higher over here, and they get lower over here. So as it's moving towards you, it's going to get higher, and as it's moving away from you, it's going to get lower. Because the wavelengths get bigger from here to here, which means that frequency is going to decrease. Wait. Is that right? I think that's right. Vector calculus is overrated. Yes and no. I don't really know what you mean by overrated. Like, what do you think? What do you think about it? You think that people think it's too hard? Too easy? Not useful? Like, overrated sort of implies the average person thinks it's good. And I don't think the average person thinks vector calculus is good. Is this right? Wait, when it's moving, if you're here, this is my great drawing of you. That's you, chat. Here, wait, it's moving towards chat, actually. I can draw chat. That's chat. They should just put chat in every physics problem. Why don't they do that? If it's moving here, the wavelength, okay, v equals lambda f. So the wavelengths are getting smaller, so the frequency gets higher, which is, yeah, that's real. And then if v equals lambda f, the wavelengths are getting bigger, so the frequency goes lower. Look at that, great. Okay, anyway. All of this is bananas. Get out of here. There are like 4 different equations we use, right? So if it is a... Oh. No way. He wants us to memorize these? Bruh. Oh god, that's so stupid. No way. Does he want us to derive them? Wait a second. Wait a sec. Oh no, okay. Okay. Oh, I got so scared. It's like, no way. No way does he want us to derive these. Okay. I was looking at the equation sheet that we get to use. So if source is moving, then, so this is going to be, right, we want it to get lower, which means we want it to go away from us. And if the source is moving, then that's going to be f0 over 1 plus vs over v, which translates to the original frequency, 25 times 10 to the 3rd hertz over 1 plus the velocity of the source, which is what we're trying to find, over the velocity of sound in a vacuum. These are sound waves. If they were electromagnetic waves, that'd be different. But, and that's going to equal the new thing, which is our 20 times 10 to the 3 hertz. Cool. So now we just gotta do a little multiplying. So 25 times 10 to the 3 hertz equals over 20. Right, 10 to the 3 hertz, that's how that works. 1 plus Vs over 343. 25 over 20 is 5 over 4 minus 1. What's 5 over 4 minus 1/3? Well, Vs equals 1/4? 343? What is that? I don't know what that is off the top of my head. I'm not a calculator. That's 85.75. I feel like that's the wrong answer. Let me check. Did I do my algebra wrong? Damie VTutor. It's so shit at algebra. Huh. Oh, it's 25. If I do 26, that would be, oh, that would be different, wouldn't it? No, that's right. I did it right. Awesome. So good at things, guys. I'm so good at things. I'm like fine at things. No one can really be so good at things all the time. It's 85. What did I say? 85.75? So can a bat fly at 85.75 meters per second? Maybe. What is that in miles per hour? 85.75. Okay, that's 191 miles per hour. I don't think a bat can fly that fast. Gonna go out on a limb? I don't think that's possible. Not sure. Show me a bat. Maybe a bat that's like this big. Like he's this big. I think this bat could do it, and here are his legs. There are his eyes. Let me maybe accurately draw this a little. This is an accurate bat. Wait, those are his legs. There we go. This, yeah, we're designing the perfect bat here. He needs to be able to fly at 191 meter. Oh my god, 191 meters per second would be crazy. This wing is bigger than this wing on purpose. He's training that one right now. The other one's just a little behind. He's determined to have humans here. His echolocation. These are his determined eyes. I think he can do it. I believe in him. I believe in him. Look at him. He's so determined. He learned physics just so he could figure out how. He's like, I need to fly away to get my... Dude, you'd have to go so fast. I mean, maybe if you just went in an airplane or something. That could work. Okay. Okay, oh, we have a little snapshot graph. I just took a screenshot of nothing, somehow. Here we go. I just love that I can copy and paste stuff in. That's so sweet. Okay. Alright. Snapshot graph of a 5 hertz wave. 5 hertz. Here on the left. What is the wave speed? Alright, that is a great question. What is the wave speed? Well, we gotta find the wavelength for that. Right? So, this looks like kind of at, 0.5 here. So I would say, pretty, just by looking with my eyes, I think that's about 2, right? So I think lambda is 2 meters. So then V equals 10 meters per second. To the left. To the left. All right. What is the phase constant? Okay. I'm not going to divide 2 by 2 equals 0, like I did before. That's not going to happen. We're looking for the phase constant. All right, we got to set up our equation. That's going to be dxt equals a sine a bunch of stuff. It's basically going to all go down to just 5. There's nothing else in there. That's fine. That's 5. Actually, I don't know if it's phi or phi. Phi, phi, fo, fum, whatever. All right. So this is in millimeters, right? So this is 0.5 millimeters equals 0.0005 meters. Because we go 1, 2, 3, and that's 0.5. Jesus. So d of 0, 0. So at 0 and time is 0. We're going to have, like all this stuff will cancel out in here because there is something, this is number times x, nope. Yeah, x plus or minus omega t, and that will cancel, equals 0. My brain is sick there. 0.0005. Getting to the point where it's too many zeros, you know? Equals our A, which is going to be amplitude is 1, 0.001 meter times sine of phi. Okay. Now everybody hold the phone. We gotta do some math. Yeah, this is 1/2. So sine of phi equals 1/2. Now that's awesome. That's great. I love it. What's that mean? We look at our unit. Sine is up and down. Okay, that's pi over 6. Or negative pi over 6. Okay? We're getting there. Oh, my back. Okay. So we've got 2 choices. Now we gotta do a little. We gotta do a little the derivative. Okay, v of xt equals negative a omega cos a bunch of stuff times, but we're gonna do 0, 0 again, right? So at 0, 0, what is this? That looks pretty positive. That's pretty positive, right? That's pretty positive. Cool, so that means that we need this value to be negative. So that will never actually wait. Well, no, we need this to be. Wait, is that ever negative? Wait a second. Wait a second. Cosine of pi divided by 6. That's positive. Cosine of negative pi divided by 6. That's also positive. Okay, what did I do wrong? Okay, where's the distance? It was that. That, yes. Yeah, well, let me just take 5. Yes. Sine equals 1/2 at pi over 6, right? I'm not going insane? So how do we make this pi? How do we make it positive? What the heck? What the heck? Oh no, I'm doing the bonkers thing. That's 5 pi over 6. It's over here. Sine is negative down here. Oh. Okay, so this needs to be negative 4 plus b. Thumbs up. Okay, so phi equals 5 pi over 6. Oh, okay. I think that's right. Can I check it? Maybe not. No, I can't. Awesome. It's fine. Okay, and then write the displacement equation. That's easy. We're not going to do that. That's just 2 pi over lambda x minus 2 pi f t plus 5. Everybody knows that. Should we do one more? What do we say, chat? One more and then we call it. Let's do one more. 48. Another one we can't. Ooh, this is a good one. We got explosive problem. Oh god, that might mean it's about sound waves. Never mind. No, it is. Oh. Oil explorers set off explosives to make loud sounds, then listen to the echoes. Geologists suspect there is oil under a 500-meter lake. Lake physics. Guys, this lake is named after physics. It's known that Lake Physics is carved out of a granite basin. Oh no, that means I have to Google something about granite. They detect a weak echo 0.94 seconds after exploding dynamite. If it's really oil, how deep will they have to drill into the granite to reach it? This is not Doppler, this is like reflective? Let's see. So, you know how I said we were gonna do another problem, chat? We're actually not gonna do another problem right now. We're gonna wrap up. Yeah, sorry about that, guys. Well, I did go a little bit longer today. I kind of want to get back into doing like more longer streams, but I had been, I don't know, I had just been like getting headaches when I would go over like an hour and a half, so I didn't want to like push it, but it was good. It was nice today. We just kind of hung out, just kind of did some stuff. I didn't really feel like too pressured. I think it's when I get pressured to do stuff a certain way. But this is just sort of like, I don't really have to worry about getting it right. I can just kind of, you know. And also I got to do some drafting, which is cool. Thanks for listening to my drafting. Yeah, I don't know. I will probably stream Tuesday. I do have a performance Tuesday. So maybe I won't. Maybe I'll stream Monday, actually. Wait, that would work out really well. Wait, would it? Maybe I could do like a little stream on Monday. Like an hour-long stream after my casting lab. Yeah, I'm down, because Tuesday I have a performance, so I'll probably be really tired. Yeah, and it's like a long one too. Or maybe it's multiple, I don't know. It's like an hour long. Normally our performances are like 20 minutes. Don't really know what that means. Hopefully I don't have to do stuff for an hour. I think I would probably pass out. That would be really hard. Yeah. So I'll probably see you guys Monday. That sounds like a good plan. Monday, and then we'll do more physics and probably more math. I don't even know what else I have. But yeah. Cool. So I'll see you guys then. I don't know, if you hated this new setup, let me know. I just have been trying to switch it up because I feel like I see my stream thumbnails and they're all the same thing, and I'm like, oh man, I want them to be like different, you know, like different fun and stuff. So yeah. Okay. I will see you guys Monday. Or you can get mad at me. I'm kidding. Don't get mad at me if I don't stream Monday. But yeah, I'll be back. Have a wonderful day. If your exams are coming up, good luck on exams. If you have any questions that you want me to do, always feel free to either ping me in the server or DM me. Either one is fine. Although I might not get to them, but like super quickly. So if it's a quick thing, you can always ask me on stream when I'm live. So, all right, see you guys later. Bye.